1.4, functions behaving badly, has a lot to do with what happens when functions are behaving not normally. So when we have things that don't usually occur. The first thing that we're going to talk about is domain. So domain is all about what values x can be. So, what x can be. Now, obviously, x could be some other variable like r or t or something else, but it's whatever your independent variable is going to be. Now, usually the only things that are going to stop your domain, there's 3 things, and the third one is not going to come up for a little bit. The first thing is going to be, you can't divide by 0. So anytime an x value allows us to divide by 0, we're going to have something happen that is not usual. 2, can't take the even root of a negative number. So let me give you an example of a couple of these. So like, again, can't divide by 0. We can't have a situation where we have like 1 over 0. And for 2, we can't, take the square root of a negative number. We can't do that. So any x values that allow us to do that, we cannot allow that to happen. So that's going to restrict our domain. And the third is, can't take a logarithm of a non-positive. This won't come up for a little while. But basically, if there's a number inside of a logarithm, it's going to have to be bigger than 0. So that would be, something that would break that would be like, again, like the log of 0. That we can't do that. So those are really the only things that can really come up. Now, most of the time with functions, that's not an issue. However, we can actually make this a little more complex by bringing in what's called a piecewise function. So let me open up the next thing. So a piecewise function, what is that? So this is kind of like us stitching together different parts of a function. So I'm going to pretend, and I'm going to make one, so that you guys can see what this is exactly like. So I'm going to pick, and I'm going to sketch this to the best of my ability, a function, and I'm going to call it g of x. So you're going to see g of x, and then you'll normally see kind of like this little bracket type guy. Now the bracket is going to do a couple of different things for us. It's going to tell us what functions there are and where they behave a certain way. So think of this as we're doing this in pieces. So piecewise functions work like this. So let's start off and say my function is going to behave like the function negative x. So you're going to see negative x and then comma. I'm going to say, okay, it's only going to do this when x is less than negative 1. So what I have to so just think about that right now. So negative x is like this. It's a line that is negative. And it goes through the center and it changes like that. But we're only looking at when x is less than negative 1. So we've got to think about what this really means. So if we think about, so up to this point or so, that's what it's going to look like. Now just imagine that this is negative 1. Okay? So our function value is going to pretend like it's negative x when x is less than negative 1. After that, it can be anything. Okay? Now, let's say my next function is going to be, let's call it, let's say it's 2. And that's going to be when x is less than or equal to or greater than or equal to 1 and less than, or -1 and less than 1. So from -1, when x is -1, so this part here, we, instead of taking on the value of 1, which we would have where that open circle is, we now move up to 2. Oops. So that is a filled circle. It doesn't have to be filled. I mean, the domains can do all sorts of different things, but I'm just creating this as I go. Now, it takes on the value 2. So 2 is just a horizontal line, so I'm going to go straight over. And now look that I don't actually, x is not allowed to be 1 here, so I've got a circle. So again, another thing. So this function changes what it is depending on what x values it is. It's not consistent, and that's okay. It doesn't have to be. And let's look at, let's say, our last one. Let's say that our function is going to be x. Okay? We'll say our function is going to be x. And this is going to be when x is greater than or equal to regular 1. So at this point, if we plugged a 1 in, we would get 1. So we know that we're down here, and we're shooting off in this direction. So this is an example of a piecewise function. Now we can look at this and try to determine all sorts of things, like what the range is, what the domain is, any kind of weird stuff happening, but this graph is very atypical because we've kind of pieced it together. So if we were to look at the domain of this, the main thing that you're going to look at is this side here. So what values is x not allowed to be? If there's anything in there that x is not allowed to be, then that would be removed from the domain. In this case, this includes all numbers less than -1, every number from -1 to 1, and every number greater than 1, or equal to 1. So this one actually includes everything. So this would be all real numbers. But it doesn't always have to be that way. So just make sure you're paying attention to what values things can be. Think about the sketches, but learn how to read these correctly, and we'll work on these in class as well. Okay, so we talked about domain, how to determine domain. So remember, we can't divide by 0, so any x values that make that happen are not going to work. So a lot of times when we, if we're trying to check domain, use the, first of all, use the rules. Okay, so use those rules. Think about, are we dividing? Do we have square roots? Then go ahead and write those things down, and we can actually figure out what you're going to do. Quick example of that, if we have, y equals the square root of x. Well, we know that you can't have, a square root of a negative number. So we know, right off the bat, that x is going to have to be greater than or equal to 0, all right? So that's a domain, right? Whatever's on the inside of the square root, that's what's got to be. It's got to be greater than or equal to 0. Just like if there's anything in the denominator, that's not going to be allowed to equal 0. Okay? The next would be our y-intercept. So y-intercept is going to be, when x equals 0. Perfect, right? So whatever the value is when x equals 0, that's your y-intercept. It's not confusing. That's all you have to do. Now there's two different things that you're going to see, and one is called a vertical asymptote. Oops. A vertical asymptote, and there's also a horizontal asymptote. These are special features of the graph. So a vertical asymptote, just to give you a picture of what this might look like, would be something like this. You see how there's basically kind of like a force field. There's a vertical line, an invisible vertical line, that our graph is not going to have. Now this is going to occur pretty much only in one case, and that is when we're going to divide by 0. So that's when we're looking, this happens here when, let's say if we plug in a number, like we see an x value, if we end up with a number over 0, so, non-zero. Any number at all. Doesn't matter if it's -1,000,000 or -0.5. If it's dividing by 0, then we're all golden. So that will come up a lot, and we'll talk about that shortly. Our horizontal asymptote, this one's a little bit different. This is going to happen when we end up with either the same degree or the denominator has a denominator, hold on, has a larger degree. Let me give you 2 examples really quick. So let's say, in the instance y equals, 2x over x. So they have the same degree. So what we do is we look at, what's the degree of the top and what's the degree of the bottom. And we only look at the top terms. So in this case, it's very simple, 2x and x. If there's anything else there that was of lower degree, it wouldn't matter. But in this case, we would take these and sort of kind of cancel these out and think, well, our horizontal asymptote is going to be 2, or 2 divided by 1. So eventually this graph is going to tend to be 2. So that we'll explain and show some graphs of that in class. And then the other case would be, let's say if we have, 1 over x. So the degree in the denominator is lower. What happens is that when x gets bigger and bigger and bigger, this is going to always tend to go to 0. So like this graph, for instance, sort of looks like this. If you look at to the right and to the left, they sort of coast towards the x-axis. And that's because as the denominator gets bigger and the numerator kind of stays fixed, it's going to always smash itself down to 0. So these are 2 big concepts that we'll keep going over, but these are special cases where things don't always work like what they should. And then the very, very last thing we'll talk about are transformations. So transformations work kind of like in the following way. So let's say we start with f of x. If we were to get f of x minus 1 or f of x plus 1, if we were to add some number into the inside, this is going to shift. This is a shift to the right, and this is a shift to the left. Now you may say, well, if I'm adding 1, why is it shifting away? So the way that you kind of want to think about this is, if we compare, let's say these two right here, f of x and f of x plus 1. So in order for, let's say if we're talking about f of 5, well, for the top graph, x has to be 5, right, in order to match that. But for this one, x has to be 4. It actually is going to get to that place quicker because it's got that plus 1 to it. It's like a handicap, so it's getting there quicker. So that's how that works. And likewise to the right, x has to be a little bit larger than it did before. And really our only other one that you're going to see for now is if we have like, f of x plus 1 on the outside, and f of x, or why don't I keep this consistent? Sorry if you wrote that down too quick. F of x minus 1 and f of x plus 1. Well, f of x, the minus 1 on the outside is a shift down, and this is a shift up. So we're adding a number on at the end. So remember, f of x and most of our functions are kind of our y value of sorts. So if we're subtracting a number at the end or adding a number at the end, that's going to move it up or down.